Lisenfeld on the two-level system and Decoherence.
Yeah, thank you very much. And welcome to the last lecture about experimental insights on two-level system defects. Yeah, so today I'll just continue with some experiments you can do with superconducting quantum bits to learn about two-level system defects. And yeah, we'll also present a few more like fancy experiments, more exotic things people could try to understand or control somehow better these TLS. So one thing that we can do with a superconducting quantum bit when it contains a TLS in its chosen junction. You have seen this picture before. This is the spectroscopy of a superconducting quantum bit, where basically you change the flux bias and you tune the resonance frequency of this qubit. So you expect basically that the frequency at which the qubit has its energy transition decreases here along such a line. But you also saw this one-level crossing here, which means that some other quantum system is strongly interacting with this qubit, and well, we more or less know, we're very sure that this is a TLS defect, which is inside the tunnel barrier of this chosen junction. This is just already clear because of the strong coupling, which gives this rise to this rather large one-level crossing here. So this can only be a TLS in the junction where the electric field is strong enough such that you get this strong interaction between the qubit state and the TLS. So the interesting thing is now that you can actually drive the TLS directly by using a dedicated microwave and its resonance frequency. So the idea is that you just use a relatively strong microwave pulse at the frequency of which you know the TLS is resonant with, just at this level crossing. And then, while you do this, the qubit is basically out of the game. The qubit is detuned far away from this TLS, so that the tuning here is large enough such that there's no any more influence of this qubit here on this TLS. So, and if you now are able to drive this TLS, you should of course also be able to measure this TLS. This is actually possible by using the qubit now as a detector for the TLS quantum state. So the idea is you drive the TLS directly with some microwave, and then after you did this, you just take the qubit, which is in the ground state, you bring it in resonance with the TLS using flux pulse tuning, and then you get the swap oscillations. So the quantum state is actually swapping between TLS and qubit back and forth. So to read out the TLS, you just go in resonance with the TLS, wait for this swap operation, and then you can directly measure the qubit, and you have now found that the TLS was in its ground or in its excited state. And so this means now you can directly use this TLS as like it would be a qubit that you can control. You can control it, you can read it out, so it's like a qubit that you have. And you can do now all these experiments which are standard for superconducting quantum bits. For example, you can directly observe the Rabi oscillation in this TLS just by changing the driving length. So we change the duration of the driving pulse here, and after this pulse we, as I said, just use the qubit to read out by swapping into the TLS resonance and measuring the qubit. You can also, of course, do energy relaxation measurements directly. So this is the measurement where you populate the TLS with a pi pulse, you wait some time during which the TLS may lose its energy, and then again, after a variable time, you just read out what's left in the TLS. And you get this typical exponential decay. You can now also, because you have this direct control, do multi-pulse sequences. So this means you can do, for example, a Ramsey experiment, for which you need 2 pi-half pulses. Again, that requires some time delay, and also you can see that this is now not Rabi oscillation, but Ramsey oscillation. And of course, more fancy experiments are also possible, like spin echo. Here you basically use, in between this Ramsey sequence, a pi pulse, which kind of refocuses the dephasing, if you wish, and accordingly you get a different dephasing time. So you can just fit all these data and then get a nice direct measurement of all these intrinsic decoherence rates the TLS experiences. So this is actually nice because now we can do what Laura already mentioned in the morning. We can now study the environment of a TLS. So you know that when you look at decoherence, the relevant decoherence rates here basically are given by the spectral density of the environment. So this is noise spectral density of the environment. And depending on your experiment that you do, for example, the T1 experiment or individualization, we know that this relevant spectral noise density is the noise at the transition frequency of the TLS. The prefactor here is just like we know from the golden rule, some coupling matrix element to the power of 2. This is the matrix element, let's say, of this TLS. And now, in the last lecture also, you heard that we have nice control over the TLS because we can tune it by applying some mechanical strain. So we tune, for example, the TLS frequency by changing the strain to this hyperbola here, and here you have the harmonic, this is the symmetric download potential, which is just given by the delta, and otherwise you have this linear tail here. So by changing the strain here, also you basically you rotate the eigenbasis of this TLS. So you can understand that at this point here we have no symmetry energy. This matrix element will basically be 0 because there is simply no symmetry energy, and this just leaves you then with this coupling, which is basically the one telling you, well, giving you the information about the switching of these states. So for the, as I said, for initialization, the relevant noise spectral density is the one at the resonance frequency of the TLS, or the transition frequency. For the phasing, it's actually the low frequency noise, as we've already nicely heard today. Especially for Ramsey, this is basically the noise at 0 frequency. If you do like multiple sequences like spin echo or the CPMG sequence, then you can also step up this relevant noise frequencies a little bit. But in principle, you're always sensitive to the low frequency noise. And now this means actually that you can use this single TLS as a, if you wish, quantum spectrum analyzer. You can use it by measuring its decoherence rates to look in the local environment of this TLS. And yeah, this we actually did at some point. Just to mention it again, the decoherence rate, T1 and its energy utilization rate, with relevant frequencies at high frequencies, and this one at low frequencies. And these are now typical pictures that we observe on these TLS. You see here 4 different columns. Each column is basically one TLS that we just characterized. First, we measured the resonance frequency of these different TLS as a function of the applied strain. Here now already expressed as the symmetry energy. And then basically here you can see the energy relaxation rate that we do measure with this T1 decay experiment. And we got these interesting curves here, which all are obviously kind of very different for each of these TLS. But it's also striking that all these curves have a very high symmetry. So they are all symmetric with respect to this symmetry point of the TLS. And okay, I told you that the energy relaxation rate is basically a measure of the noise spectral density the TLS sees. And of course you can understand that in the amorphous material, all TLS are different, each has its own very unique environment, and that's why we naturally would expect that, as we have already heard as a question in the lecture before, that each TLS should see a different phonon spectrum. And we believe that this is exactly what we see here, because obviously all these curves are rather different, so each TLS sees somehow a different noise. And the fact that these curves are symmetric already tells us that this cannot be due to interactions with other TLS. Because TLS all are changed by the mechanical strain, as you see here in these other TLS in the background. So if the interaction, if this energy relaxation would be determined by the coupling to other TLS, we would not expect any symmetry here, because well, the other TLS in the background simply are not, don't also have the symmetry point at the same spot here. And actually, what we also did further, you can then basically just plot all these rates here as now a spectral noise density as a function of frequency, and put them all over another. And basically, then you see that some of these curves do have a common peak at some frequency, which we believe is actually kind of a standing wave, also in the torus junction. The torus junction had like a size of 1 micrometer square. And if you, well, do the calculation using the phonon velocity, you find that there is actually a resonance at a certain frequency at which all of these curves also show a small peak. But this is not the only peak you see. You see a additional structure here, which is that we believe are the phonon modes in the local environment of this TLS. If you look at the phasing, then first of all you see that at zero symmetry energy of the TLS, or at the symmetry point, you get zero defacing. This is a defacing rate here. The blue one is the random defacing rate. The green one is the one which I measured by spinning. And it's clear that we assume that at for symmetric TLS, you would not expect any defacing to occur, simply because you're kind of operating at a sweet spot here. Yeah? So I mean, if you're at this point, small changes of the symmetry energy will in first order not change anything. So that's why we naturally expect a minimum of the defacing rate here at the symmetry point of the TLS, and this is what we see. And then, of course, you can think further what determines these curves here, and also those are not always the same shape. This is maybe more linear, this could be more quadratic, but we have a theory for that which actually goes like that. So the idea is that the defacing rate of a TLS is mostly determined by the next neighboring thermal fluctuator. So thermal fluctuators, you heard, are just other TLS which have small energy such that they are thermally fluctuating between their states, like classical telegraphic fluctuators. And they can, of course, change, for example, the symmetry energy of the high frequency defect that we are measuring here.
Sorry, are you saying that it's nonlinear? The fact that you have finite maximum is nonlinear effect?
I don't think I'm saying that, but just listen to what I'm saying.
You said that.
That it's a nonlinear effect.
Yeah, because you said that linear, if I just believe that this is in a linear response, then because you have a maximum, then T2 will be infinite. Because dividing by 0 gives you infinite. Right?
Okay, so I think I said that this looks
so
linear.
Then you started to say something about that you have telegraphic noise, and so you meant that this is nonlinear effect?
Well, I said that this looks more linear and this looks more quadratic, and then I was
No, I'm just talking about the fact that at maximum, if the T2 star is finite at the maximum, then in your plots, in all of your plots.
The T2 star is finite.
It's a maximum. You have a sharp maximum. That's very good.
Yes. It's of course finite. Yeah, it's limited by the T1 time. So this this dashed line here indicates twice the T1 time. And of course, you know the defacing time cannot exceed twice the T1 time.
No, you explained, right?
Huh?
And I think correctly, that there is a very special point here, right?
Yes.
And here, where your T2 has maximum.
Yes, that's correct.
And then you showed us this slide, no, maybe the previous slide here, and you said that this is maximum. And this is maximum because here the derivative is 0, which is clear, right?
Yeah.
So now I'm asking you if it is why it's not infinite here. What makes it?
Yes.
So if I divide by 0, I get infinite, right?
Well, the maximum T2 time which you can get in any system is twice the T1 time. You agree with that, right?
No, but that's T2 star, I believe, no?
Sorry, this is the T2 star which I just measured. But of course, it's the dashed line here is twice the T1 time. So this is just the observed T2 time, just see the time, the real time. It's not the rate. The rate is 0 here. This is what you mean by infinite. The inverse of this is infinite. That's correct.
So it's really experimentally infinite. No. If you
the experimentally observed T2 time at this point is twice the T1 time exactly.
So that T2 star is infinite, in other words.
The phasing rate is 0, yeah. If you wish, you can say T2 star is infinite.
Okay.
Thanks for the question. Right, so the theory goes that we basically assume that the dephasing of this TLS is dominated by the next nearest thermal fluctuator in the vicinity of this TLS, right? Which makes also some kind of sense, because the next nearest one is the one which has the strongest influence on the asymmetry energy. So, and this actually now means if you have only a single thermal fluctuator in the vicinity of this TLS, you would actually expect that this single fluctuator generates telegraphic noise. If you think about that, telegraphic noise should result in such a linear increase of the dephasing rate for TLS, which we actually observe here. So in the small range, here, not all everywhere, but at least somewhere, we see some linear scaling here of the dephasing rate. with just the energy. And this can be explained by a single telegraphic noise fluctuator in the vicinity of this TLS. It can, of course, also be that, and actually a nice point is that here you see a change of the slope. It seems maybe still linear, but the slope is different here. And actually we explain this by the fact that while we tune the strain here, we of course also tune the thermal fluctuators around, so also their frequencies are changed. And this means that we can now, by the strain, bring a thermal fluctuator out of the thermal bath. So it will stop to fluctuate at some point. But you can tune at the same time another TLS, maybe also in the vicinity of the TLS, of this special TLS, down in the thermal bath, below kVt. And so the idea is then that this change of slope just means that now we have another dominating thermal fluctuator, which maybe has a higher fluctuation rate or stronger coupling to this TLS, which we measure here, such that we still get this linear tail here, but now with a different slope. Yeah, and to explain more of this, and actually also another interesting point here is you see that this dephasing rate from the spin echo sequence is completely zero, yeah, or T2 star is infinite. And this is actually also reasonable because if you have only a single thermal fluctuator, a single telegraphic fluctuator, which affects the dephasing, we can nicely correct by just the single refocusing pulse, which is used in the spin echo sequence. Right, and to explain more this parabolic part here, we actually just assume that here more than one thermal fluctuator must be in the game. So this can be explained by just like a sum of many of these, or some kind of combination of many of these linear contributions, giving more this parabolic or kind of quadratic term. But of course, in fact, it can have any shape. Also here you see it also decreases at some point again, because basically we think that all dominating TLF in the vicinity are basically brought out of the thermal bath. Okay, so a nice experiment actually to provide another point of view into this coupling of TLS to the phonon bath. I told you that, well, you know already that the energy relaxation of a TLS is mostly dominated by its coupling to the phonon bath, which is the strongest coupling we have in such a TLS. And now this group from Oscar Painter actually tried to probe this by making a choices junction which contained these TLS, which you could also then nicely measure using these techniques which I showed you. There's actually a qubit, or it's like operated like a qubit, so you can just do a measure for the coupling and the anti-crossings, and from this also observe the T1 time of this TLS. And now this junction is actually fabricated on a so-called acoustic metamaterial or phononic bandgap material. So this is actually like a membrane of silicon, which is like free-hanging, and it was etched into this regular structure of like squares, which are well, weakly connected to each other. And you can imagine that in such a structure you have a very specific phonon spectrum. Most importantly, at a certain frequency you expect to have like no phonon modes. Basically these are these frequencies where the phonon wavelength is somehow compatible with the size of these islands here. So you can do some calculation of such a phononic bandgap material. And this is a phonon spectrum that you would find in theory, and you see it's designed such that we have a gap here between 4 and 5 or 4 and 6 gigahertz. And now these people were just measuring the runtime of this TLS as a function of frequency, but just looking at different TLS which have different frequencies, and then they see that indeed within this band gap the TLS have a significantly higher T1 time than if you look at TLS which are not inside this band gap. Yeah, this is of course another demonstration how you can demonstrate that this phonon coupling is really the dominant decoherence mechanism. So now, since we have this nice control over the TLS, we can also look at the temperature dependence of the TLS coherence times. And just to talk about the T1 time in this lecture. So you see, this is the T1 time which you measured from a TLS as a function of the Kreisdorf temperature. it was an unexpected result because, well, we of course expected to have some cotangents with body cost dependence here, which you just expect from the phonon coupling. However, we saw a more steep dependence here. So at higher energies, higher temperatures actually have an even smaller T1 time than we would expect from the simplest formula. And then actually it turns out that you could fit such a curve by not thinking only about the phonons, but also taking the quasi-particles into the game. So quasi-particles, you know, are the Cooper pairs which are broken due to enough thermal energy, and this quasi-particle density is an exponential function of the temperature. So by just adding some exponentially dependent rate here on this T1 TLS decay rate, you can actually nicely fit such a curve. So this black line here is now just the sum of this cotangents dependence plus some exponential on temperature, which is proportional to the quasi-particle density by a small constant factor. So the idea here is that these TLS could also see T1 decay due to their interaction with quasi-particles. So the idea here is that we have these TLS in the junction, the tunnel barrier. Here in the superconducting electrodes, you have this quasi-particle density, it just depends your exponentially on the temperature. And these, of course, may just move along this line here. They have, of course, some probability to be also inside this tunnel barrier. And then they could, of course, also scatter tunnel through the junction. And by doing so, they actually could interact with this TLS and basically scatter on this TLS.
As far as I know, there's been some study of actual concentration of quasi-particles in such systems. And there are separate problems with the fact that they are not thermal, in fact,
Yes.
which begs the question whether you try to compare, let's say, the independent estimation of quasi-particle concentration with this plot.
Yes, this is a valid point. In fact, we always see like a background excess density of TLS. Of quasi-particles. We are not yet sure where it comes from, maybe cosmic radiation, but okay, it's an open question.
Yeah, I'm just saying that
yes.
If you see the excess density of quasi-particles, you can probably detect them by an independent measurement and compare this with this plot, and this will immediately tell you whether this is indeed quasi-particles, be it thermal or not.
Well, we could detect this, but in principle, I would assume that if you have this excess quasi-particle density, we just get some offset here in the decay rate. So I mean, this is just the offset of the already existing quasi-particles, to which in addition we add these quasi-particles by heating up the junction. Okay, so the idea here is now, could these temperature dependence of this TLS be explained by quasi-particle interaction? And this is actually a reasonable assumption, first of all, because this dependence here, well, as good as the data gets, more or less fits this idea. So, in the set, this is just an expansion dependence here of the quasi-particle density scaled by some constant factor. And also, of course, people already knew from the classic experiments on the bulk classes that TLS do interact with quasi-particles. This was possible by just taking a bulk superconducting metallic glass. So there's glasses which contains metals, and of course you can then also make a glass out of a superconducting metal, and then you can just, for example, make a mechanical resonator, as I showed you in the last lecture, measure the T1 time of these TLS, and then you could actually break the Cooper pairs, for example, by some magnetic field above the equilibrium field of the superconductor. So you change the quasi-particle density by this way. And this was very clear that, yes, indeed, these TLS do interact with quasi-particles. So to see how much they interact with quasi-particles here in such a junction, we did a further experiment where we actually used two qubits on the chip. So these are actually more ancient qubits, let's say. These are phase qubits, which are actually fabricated in a Martinez group, and I was lucky enough to get one of these samples during my PhD thesis. So what we did is we operated one of these phase qubits basically just as this TLS detector, measured here the TLS coherence times in the junctions of this qubit, and then we controlled the quasi-particle density basically by only using the readout DC split. The readout DC split of this other qubit here which is basically just a junction which is connected to some voltage line, some current bias here. So we just use the thesis grid here as like an injector for quasi-particles. If you bias a junction above its critical current, then quasi-particles will be produced. And the idea is that we just generate a current pulse here, then we will generate quasi-particles at this point here. These quasi-particles will diffuse over the tip, and then at some point reach this junction here. And then of course, yeah, then we should expect that if you now have a TLS in this junction, these quasi-particles generated here will at some point change the T1 time of this TLS. And this is also, and to do this, to quantify now the quasi-particle density as a function of, for example, this current which we sent here. We can do the following experiment. We now first measure the qubit T1 time. I think they have some timer active here. So the qubit T1 time is also like a measure for the quasi-particle density. This is also well known theory by Catalani. So more quasi-particles, you have also the smaller the qubit T1 time. So you can use the measurement of the qubit T1 time as now a probe for the quasi-particle density, and to calibrate basically your quasi-particle density as a function of the current which you apply here, or also as a function of the mixing chamber temperature. So we find that the quasi-particle density as a function of the driving current here, which is this green data point, is just linear above a certain point. This point is also clear. This is the critical current of the junction, and this is just the linear slope from the fitting factor. And this exponential factor basically is works more or less without fitting factor. It's just the thermal dependence of the quasi-particle density. So now having this calibration, we know pretty much exactly what quasi-particle densities we have. And now we can just go on and measure the decay rate of the TLS as a function of this quasi-particle density. And indeed, we see that there is an increase. So there's a linear increase, which is also expected. This is like Fourier relaxation. So the relaxation rate is just linear proportional to this density of quasi-particles, plus of course some background decay, which could also be due to some background quasi-particle density. There's an interesting point, because actually we see that when we measure for the same TLS the decay rate into thermal and injected quasi-particles, we do get different slopes here. This is a subtle point, but we think we understand it. The point is actually that the coupling of a TLS to the quasi-particles depends on the position of the TLS. And you can imagine, if you make thermal quasi-particles, we heat up everything, so quasi-particles will be generated here and also there. So a TLS would just see the same kind of density of quasi-particles coming from this side, like from this side. However, when we inject quasi-particles, we inject them at the ground plane of the chip. So this means quasi-particles are injected only in one electrode. Of course, they can tunnel through, so there's also some density here, but mostly they're just on one electrode. And this is why we believe this can explain this difference of the decay rates depending on the thermal and the injected quasi-particles. And actually we use this further to try to really pinpoint the position of the TLS in the tunnel barrier, just seeing whether it's close to one electrode or the other electrode. This can actually also be helpful for experimentalists to fabricate these TLS, these qubits, because then you can understand whether your TLS are mostly on the top electrode or mostly on the bottom electrode.
Can it also be the case that, for instance, the particles that you injected manually, they just didn't, let's say, have enough time to diffuse properly until the...
Yes.
I mean, even at the one side of your electrode.
Yes, I mean, actually, as I said, we inject the quasi-particles to the ground plane here.
Yes.
And the upper electrode of the junction is only connected through this thin tunnel barrier, and of course through this very long inductance here. This is a phase qubit where it's actually a huge and very long line here. So in order to have a quasi-particle come really to the other side, either it must tunnel or it must go this very long path.
No, I'm saying even not on the other side, but let's say you create your quasi-particles on this left side of your device, and they inevitably take some time to diffuse, basically. So I'm not aware of how large this time exactly is. So, but maybe it is the case that just they do not enough time to they do not have enough time to reach their device in their
Yes,
full concentration.
We also observed this rise of the, for example, this decrease of the decay time is a function of time after the injection pass.
Yeah.
So you could actually measure directly this time constant which you talked about, and it was a few, if I'm not mistaken, now 100 microseconds.
Okay. So it saturates already, right? So what you are showing already saturates.
It was saturated, yes. But this is a very good point, and we made sure that this is not anymore a drain sand effect.
Okay.
Nice. Okay, so I have in the last talk already talked a lot about mechanical strain tuning. So, and for this, just to remind you, we used this piezo by which we just deform the chip a little bit, we bend the chip, and then we could observe here the TLS hyperbolus basically as a function of the symmetry energy in the T1 time decrease of the qubit. Yeah, so these dark pixels are just the points where the qubit is in resonance with this TLS. This is why it has a short T1 time. And now in the following, I'm going to talk more about electric field tuning. This is the second way how we can talk to TLS. And for this, I already mentioned that we had some electrodes in the vicinity of this qubit chip. Just again connected with some voltage source. So applying some voltage here, definitely everything would here somewhat be exposed to some electric field. Okay, this is an old slide, right? So now you see here the electric field dependence in the same measurement like here. This is actually also the same qubit, same chip. I just actually stopped at some point here and then continued to keep the strain fixed, but varied the electric field further.
Another question.
Mm-hmm. Yeah.
So in those plots, you show, let's say, how the spectrum is also the function of voltage as you tune it, let's say, up. Did you check whether if you tune it back down after that, if the spectral remains identically the same?
You are talking about...
No, about, let's say, the very big shot.
Oh, yeah, I understand.
So
yes,
whether there's some hysteresis
yes.
because of
Very good point also. Yes, I did this, of course. We do find some hysteresis for some TLS, but not all. For most TLS, actually not so much. Some show rather significant hysteresis. And this is also understandable, of course, because you may have like meter-stable TLS. Yeah, we tune them by the strain. At some point, they just jump in the lower valve, and they locally change the strain, for example. Yeah. And then, of course, you need more strain to go back, and then have the tunneling back again. Right. So we did observe this, but yeah, in general, I can say that these measurements are rather really stable. I mean, you can do such a measurement over like a month, and you will find mostly the same TLS. Of course, there are fluctuations because there's thermal TLS changing their states, and yeah, so there's this little bit hysteresis, which again just tells you about the meter-stable states in the environment. Okay, so right. So now this on this right side here you see the electric field dependence, and here you see the strain dependence. I mean, there's a striking difference, right? The right picture you see many lines which do not depend on the electric field. And we know already that these are also TLS because we can tune them by the mechanical strain. And it's there's no way how any other resonance in the circuit depends on the mechanical strain. Like you could have a parasitic resonance in the circuit, but it's a macroscopic thing, and the strain which you apply is really minute. So there is simply no reason to believe that anything else would depend on strain here. Only the TLS should depend on strain. So what happens here? Why do these TLS here? Why do only some TLS respond to the electric field and others not? So we were quite puzzled by this, but the solution was rather clear at the end. These TLS which do not couple to this applied electric field must reside in the tunnel barrier of the chosen junction. And those which do show this coupling to electric field are residing on the surface of this qubit. Why? So, of course, on the surface you have the electric field because basically this is a ground plane. Here the electric field lines like to end of this electrode, so certainly you will have some electric field on the surface. But in the chosen junction you don't have a DC electric field. At least not if you make a transform qubit. Because you know you have a transform qubit, there's a large capacitor, you have a small charging energy. So if you would have any DC electric field in the junction, just the qubit pair would tunnel to the junction to compensate this DC electric field. And this is why you will never be able to induce a DC electric field in the transform qubit junction. Yeah, and this is basically the solution now. We can nicely distinguish TLS in a junction from those on the surface. This is, of course, again, very useful for people trying to improve their qubits, because then we can understand, okay, do we have to improve the junction, do we have to improve the surface? And actually, on the first measurement we did in this way, we observed this kind of statistics. We found like 60% of TLS were on the surfaces, and a significant number, namely 40%, were in torsion junctions. And this was also very surprising, because this is not expected from the non-TLS density that we have in the material, in the small volume of the tunnel area of the small qubit junction. However, it turns out that this qubit was fabricated in a way where you don't only have the small tunnel junction which you need for the qubit, but rather you also have very large junctions in series with the small junction. And these large junctions actually are just used as kind of a connection, as kind of a via to come back here from the top electrode to the bottom electrode, which is the ground, to connect to the ground plane here. So these are really just like not necessary junctions, but they are like have a good use from the point of view to connect these small junctions. And of course, these large junctions would not play a big role in the qubit dynamics, or actually no role at all, because the smaller junction, of course, has the dominating phase difference, which basically gives rise to this plasma oscillation. So the large junction basically does not play a role in the qubit dynamics. And that's why people actually thought that, okay, it doesn't matter whether we have these large straight junctions, so why not just use them to make life easier? But yeah, in fact, it turns out it's not a good idea, because then you have like 40% of your decoherence you can expect just arise from TLS in your large straight junctions.
Maybe your problem is how exactly you distinguish where exactly of those three junctions the TLS actually is located?
You can get some idea about this, because it turns out that the coupling strength of a TLS in this small junction is much larger than the coupling strength of the qubit of the TLS in this large junction. The reason is simply that you can think about two capacitors connected in series, a very small capacitor and a very large capacitor. The relevant voltage drop will occur over the small capacitor. So this means that the voltage in the small junction is basically by a factor larger than this large junction, which is just the ratio of the areas of these junctions. And this area ratio is like a factor of 200. So if you would assume that these junctions, these TLS here are a small junction, they would have a much stronger, much higher coupling strength. They would not generate these rather thin lines, they would like generate really thick lines. And you will see some examples later. And yeah, this is one argument. The other argument is simply, as I said, it's not reasonable to assume that we have so many TLS as you see here actually in this small qubit junction. So in principle, you don't need these straight junctions, and I told you we should avoid them. And of course, there's a technique for that. You can basically just short these straight junctions by using a piece of metal, so some metal strip here placed over this junction to short it, and then basically you switch off this junction. And if you do this experiment on such a, actually this technique is called bandaging. It's like you put a plaster over the straight junction just to get rid of it. And if you do this now with the so-called bandaged junction, a bandaged qubit, you see in fact that you see in the electric field tuning a much smaller density of these TLS which do not respond to the electric field, so which are junction TLS. And now also this is a much wider frequency range here compared to this one here. So this is actually much more seldom now to still find a TLS in the chosen junction if you make sure that you have only the small qubit junction. So actually the number of TLS which you should find in such a junction is typically about 0.1 every 0.1 per gigahertz. So meaning you have one TLS like every 10 gigahertz of frequency which you can access here. And this actually boils down to the typical density of TLS, which we know also from the classes. So these are about 1000 TLS per gigahertz and micrometer cubed.
Have you tried like doing some many qubits, some produced without state junctions, some with stage actions and see how much the cooling time increases on average.
The T1 time increase?
Yeah.
Well, from what I told you, I would expect
Yeah.
a pretty significant change. We did not do this just on a. We should do it on the same chip. We should have same chip, one code with straight junction, one code with straight junction, then you could compare them. Of course, you would still have a large spread between the T1 times, but we didn't do this. No. So what we do then often is to make systematic scans of both electric field and mechanical strain, just to see how much each TLS responds to both of these stimuli. And this is one of the example measurements we like to take. So this is again the T1 spectroscopy of the cuvette, as you see before, but now it's kind of a segmented picture, because first we started to vary the electric field by some value, then we keep the field fixed and we continue to vary the mechanical strain. Then we keep that fixed and continue to sweep up the field. And then basically what you see is these hyperbolas of the TLS, which are now kind of also segmented. They have different slopes in the different segments, whether we have field or strain. And here, for example, you see the signature of a TLS in the junction, because we have only a tuning of the TLS frequency in the strain region, because all TLS, as I told you, have a couple of strain, but there is no change in the electric field. And that's why you get this kind of staircase hyperbolas here. So this is a junction TLS. You can also identify in this picture a surface TLS which responds to both. For example, this is a nice example. You tune this TLS down by the field, up by the strain, down by the field, and up again. And then you can see how this hyperbola like zigzags all over the range. So, and then we just have to fit all these curves to these hyperbolas, which now, of course, depend on both strain and field. And we, of course, know all these values here of these voltages which we apply. And these are the fitting parameters, basically. And so this is then the result of some fitting. And yeah, by this kind of fit, we are now basically able to not only measure the gap energy of the TLS when we observe it here in such a minimum of the hyperbola, but also the coupling to the field, which is basically a measure for the electric dipole moment of the TLS, and it's coupling to the strain, which is the measure of the deformation potential. So you can get more information out of this by basically also looking at the vertical cross sections here. So if you now take one of these cross sections, again you find, of course, these relative peaks here, as I had shown you before, and you can also fit those to some equation, which is again some decay rate, which is determined by, again, the coupling strength between the cuvette and the TLS, and this is basically the sum of all decoherence rates in the coupled system. So it also contains the dephasing time and the initialization time of this TLS. So by these measurements, you basically get, as I said already, these three parameters of the TLS, plus now some information about at least the product of the coupling strength, dipole moment of the TLS, and its decoherence rate. So this means you can now do statistics, because you use many of these TLS, and you can also separate these statistics into the two classes, because you are able to distinguish junction TLS from surface TLS. And some statistics are shown here. In blue, I show the junction TLS and the surface TLS. This, for example, is the coupling strength to the strain of this TLS. Just measured as a megahertz in volts. Basically, just the slope of the TLS here, TLS hyperbola here in the strain regions. And another thing is you can observe the coupling strength of the cuvette, and you get these curves and the coherence time about 100 nanoseconds for the TLS. And the point I would like to make here is that these statistics, as good as they are, it's not really reason to believe that there's difference between these two TLS. So there's a more or less similar distribution here, and this is why we may argue that most probably these junction TLS have the same physical origin like the TLS on the surface. At least they show rather similar interaction strength with the environment, and yeah, coherence. Yeah, okay, this is just the complete raw data that was taken. I think the measurement took like 2 weeks or so, maybe even 3 weeks, and the fitting a few days, let's say. And now, coming back to your question, I told you that these TLS and the small junctions have a much larger coupling strength to the qubit. So they would generate a much broader Lorentzian diff in the T1 time. And you can see a few of them. Obviously, there's a very large strongly coupled TLS here. And this is definitely a TLS in the small junction. And you see it basically really blocks or blacks out the qubit. For example, I can measure this by starting here and swapping down. And once you swap through the strongly coupled TLS, everything here is basically lost. There's a few other ones. This is also a junction TLS, and you see how broad this resonance is with respect to these surface TLS, which have the smaller coupling. And this is also one in the small junction. Yeah, these are really insightful experiments, and yeah, it's fun to do them. Okay, now we have this control over the TLS by the electric field. And of course, you can now use this in trying to improve the T1 time of the qubit. So how can we improve the T1 time of the qubit? The idea is probably already quite kind of obvious if you look at this picture. This is again in the color code showing the T1 time of the qubit. It's a function of the applied electric field and the frequency of the qubit. So obviously, if you now say, okay, let's operate my qubit at 4.8 gigahertz, clearly it's not the best idea to do this at zero electric field, because here you have already like a bunch of TLS in resonance or near resonance with the qubit. So why not just go to applied electric field and go to a place where you are further detuned from the TLS? And yeah, this should improve the T1 time, and of course at each frequency which you would like to use, you would need to find a new optimal field, because of course everything looks different here. So this frequency, maybe it's better to go here, or this frequency, maybe not, why not go here? So this is a simple idea, and it's also a simple experiment to prove it. We just have to measure the T1 time of this qubit. Now it's a function of the electric field, so of the voltage which you apply to the electrodes. This is now the qubit T1 time, and you see it has, of course, these sharp, these dips here, because here you see the resonance of a TLS, tuned in resonance with the qubit, and there's more of them here. And the ideal point now will obviously be the one where the T1 time of the qubit is the highest value. So you basically just measure such a curve here, maybe using, I don't know, 40 or 10 different voltages here, and just find the maximum, tune the field to this maximum, and you have improved your qubit T1 time. This is simple enough, but maybe I should further give some examples that this really works. So, of course, you have to take into account also the time dependence of these TLS frequencies. They are fluctuating due to their coupling to thermal TLS. So that's why we measure the T1 time at this optimal point here, like for 30 minutes, just to get some more stable mean T1 time of the qubit. And then we compared this at the optimal field with another measurement which we did before, optimizing the field here at zero electric field. And you see at zero electric field, obviously you get a smaller T1 time even over the complete course of 30 minutes. So after optimizing the field, you actually gained something in T1, you have improvement of T1. So we can do this at different frequencies of the qubit, where always we have different TLS interacting with the qubit. And we find that, yeah, in most cases it works nicely, of course. In some cases it can be that the situation also reverses after some point because of the fluctuations. So you see this TLS somehow drifted out of the TLS spectrum, and then basically the qubit at the end is even better at this non-optimal field than it was here at the beginning, at the optimal field. Nevertheless, when we do statistics over many more frequencies, we see that on average we get a quite nice improvement of T1. So basically, this is the green dashed line here, shows on average like a 23% higher T1 time after the field optimization. And of course, in some cases, you can even get 100% higher T1 time when you optimize the field, because then you were just able to move one dominating TLS out of the resonance, which was just there in the beginning. So it's also a nice technique. Could also be useful for quantum processors. For example, if you remember the strip chip architecture, where you have two chips opposing each other. One contains the qubits, the other top chip can contain resonators or control lines, and they could also contain these DC electrodes which you need. So the idea is you have just a DC electrode above each of these qubits, then each of these electrodes is connected to its dedicated voltage line, and then you can just quantum processor at the same time, simultaneously and even independently optimize the T1 times of all these qubits in the processor. Okay. So further games you can play with electric fields is to try to figure out the point at which the TLS is actually sitting on the chip. So now I'm talking about TLS only on the surface of this qubit chip, so either the oxide here, so that, or here on an interface called the substrate metal interface. So basically the TLS which are kind of buried by the metal here on the substrate surface. And there's also the so-called substrate vacuum interface, basically just the surface of the substrate. And of course, as I told you, there may be different reasons why you have different TLS here and there. Here you may have mostly residuals, like in photoresist. Here you don't actually extract residuals if you make sure that the first thing when you do in fabrication is to clean your substrate and just put the metal on the cleaned chip without any oxide, without any photoresist. So the chip has nothing, you see nothing, only the metal. So this should be a very clean interface, and this is expectedly a rather dirty interface. This will release residuals, contamination, and anything else what can be coughed on this sample. So now, how do we find on which interfaces TLS is sitting? The idea is that we basically use two different electrodes here, which are independently controlled. One is above the chip, connected to one voltage source, the other one is below the chip, connected to another voltage source. And now, when we do the simulation of the electric fields, which are emitted by these electrodes, we see certain different spatial dependence. You see the electric field, which is generated by the top electrode, has like a hotspot, a maximum here on the top of the electrode, which is of course clear because the electrode is above the chip. So here the field lines have the shortest path to end, and the lower part is actually kind of shielded by the electrode itself. It's vice versa for the bottom electrode. Here you get the strongest field here more on the substrate metal interface and here on the substrate vacuum interface. So you have this nice difference in the field strength from the two electrodes. And now you can basically just measure how strongly each defect corresponds or responds to the top electrode and to the bottom electrode. So again, we do these kind of segmented measurements. We measure the TLS hyperbolas as a function of the voltage applied to the top electrode. And then we stop here and continue to vary the bottom electrode voltage, and you get the hyperbola with a different slope here. So these two different slopes you can just fit again. And now what you have done is you have basically measured this left part of this equation. So the ratio between the coupling to the top electrode and the bottom electrode. We expect that this just corresponds to the ratio of electric fields emitted by both electrodes. So by using the simulation, we find here this ratio of the field strength as a function of the position in space. So going along, for example, along this line here. So this means you have to know everything to try a solution for the position of the TLS here, because the Dipole moment actually drops out of the game. This one we can just measure, and the only remaining thing that we expect to have here is the position of the TLS.
You mean that ET of x above and below are simulated according to the respective distribution?
Yes. So this should be a P. This is a mistake. This should be a P, of course. Yeah. So this is just a ratio between the electric field at a certain point, either generated by the top electrode or by the bottom electrode. Okay. So here, of course, this ratio is much larger than 1. Yeah, the top electrode dominates here, and here the the ratio is smaller. Well, it's just the inverse. Yeah. So basically, here the bottom electrode dominates. Yeah, and the key point is really this kind of spatial dependence of the different fields generated by the two electrodes. And so after some analysis, we then try to solve for the position of this TLS, and this is what you get. This is kind of the probability distribution of the TLS position. Now also separated for the different interfaces. So actually what this means is the 0 point here is just this edge here, where the metal hits the surface. So this is kind of 0, and then if you go in this direction, you go up this electrode. So basically you see here, if you go in this direction, the TLS on the oxide vacuum interface, which is just this upper surface of the oxide. And you see that, in fact, we find the largest contribution of TLS seems to just lie here in the metal oxide.
What do you mean by largest contribution with respect to what quantity? Because the mere count of them is a ill-defined thing, because you can just miss some of them because they are weakly coupled and some of them are strongly coupled. So in a sense, you kind of count them within a certain range of coupling strength, and this is how you define the number.
This is totally right. This is only the distribution considering only the strongest coupled. That's
like strongest and comparable, or just strongest that you could find, because those are apparently different.
Well, the strongest ones are the ones where we can identify the hyperbola on these measurements.
Yeah.
And you're right, there may be a lot of other TLS which you just don't see in these measurements, and we have no idea where they are. Yeah. Did this answer your question?
Partially, we can discuss this afterwards.
Yeah, but it's of course a general problem. We have some cutoff for the sensitivity of the qubit to only the strongest coupled TLS. But if you assume that, if you assume that also the more weakly coupled TLS don't behave much differently than the strongest ones, I think there's no reason to believe that we would find some surprise here. If we would not.
Because let me maybe rephrase my question. Wouldn't it be more natural to, let's say, plot the distribution of something like density of TLS at this given spatial region times the average, times the coupling of this particular TLS to your qubit?
Okay, so I think I get what you mean. Well, I'm not sure this would be more reasonable.
Well, I'm not saying, I'm just asking.
Yeah. Well, maybe a point I can clarifies it. We only observe in fact TLS which are only in this vicinity of this qubit edge.
Yep.
And the reason is very similar, because also the asymmetric field of the qubit has a hotspot here, and it's basically very small if you go further up this edge. And you're totally right, and this may be really the explanation here. We cannot observe any TLS which is further away than 100 nanometers from this edge, because the qubit field is already too small there. Yep. And this also means that, I mean, I don't have the picture here, but you can also, of course, make the same solution with the asymmetric field of the qubit, and you just see it again, such a hotspot here at this point, and then a quick decrease here when you go up here. And this is, in fact, why this curve quickly decreases. Yeah, and also the second strongest distribution we find is on the substrate vacuum interface, which is also not unexpected because of all these problems you may have here. And as expected, the substrate metal interface seems to be the most clean one. As I said, this is the first one which you make, the first interface you make, so it should be the cleanest one. Nice. Okay, so we can go one step further, and we have now only measured kind of the vertical or distance from the edge, but you can also try to get a two-dimensional map of all the TLS on the qubit. So for this, we made a new qubit. It is again just a transform qubit with the chosen junctions here. And now we have addition 4 DC electrodes surrounding this qubit island. And again, we can put a voltage wires to each of these individual electrodes here. And again, of course, then measure just how strongly each of these TLS responds when we change the voltage on these 4 different electrodes. And the idea is the same. So again, we use simulations, like you should see here, to get this right part of the equation. Here again, we compare always ratios between coupling strength or ratios between electron fields, because then the electric dipole moment of the TLS automatically drops out. And yeah, basically, we have now again measured here the left part, we have simulated the right part, so we can come up with the solution for the position of this TLS. This is some examples. We always, as I said, compare ratios between 2 electrodes. And you see that for each of these pairs of electrodes, you get a set of solutions for the possible positions of the TLS. These actually are lying typically around a circle, around this electrode to which the TLS responds most strongly. And you see here that this is always the same kind of measurements in TLS, but now we just compare the different ratios, and each cross here is one valid position of the TLS where we find the same electric field strength emitted from the different electrodes. So at the end, we kind of intersect all these solutions here to come up with the intersection, and in most cases, only a few possible solutions, or even a single unique solution of the TLS position remains, which you can then say is the most likely position for this TLS. Okay, this is just the coupling strength. Yeah, and this is the final result. Now you see the real geometry of this transform qubit. This was actually an older simulation, it's not the same geometry, but this is the real one. And of course, we used the real simulation for this one. So every red pimple here on this picture is now actually the position of one TLS, which we believe where it is sitting. And again, there's some statistics. We do find a little bit more TLS on the islands, on this inner edge here of the qubit, compared to the outer edge here. And this is also not unreasonable because the electric field here on this inner edge is a bit stronger than on the outer edge. So this could explain maybe this difference here. But most strikingly, of course, the most TLS are very close to these junctions here. So there's a large excess of TLS here if you consider, for example, the density of TLS as a function of metal edge vector here. There's much more TLS here than on the island. And actually, this was not really surprising because due to the reason we discussed just before, the electric field of the qubit is concentrated near the junctions. So this is now the simulation of the asymmetric field of the qubit, by which, of course, the qubit couples with the TLS. So where this field is strong, you have a strong coupling, you see many TLS. This is again just this thing that depends on local fields and your qubit coherence, of course. Yeah, and you see the field is very much concentrated around the junctions, which is clear. The junctions is just basically this 2 nanometer gap here, and then obviously the distance between the electrodes is pretty small, meaning you get a strong field. So it's no surprise that most TLS which affect the qubit decoherence really lie here in the vicinity of the DC signal. So there is some ideas how we can mitigate this problem, and obviously we need to kind of make this field less strong near the junctions. John Martinez came up with this idea to not use straight wires connecting these islands with the ground plane, but rather these tapered wires. And this means that just here you have you make it easier for the electric field to take this longer path here, further away from the junction to close this gap here, and not all the fields are really like pushing towards the vicinity of this wall gap. So this is one idea. You should optimize the geometry to dilute the electric fields. This is a very important design criterion if you want to make a good qubit. You should make sure to minimize electric fields. In other words, this minimizes the participation ratio, which Lara mentioned in the morning. So participation ratio is kind of the energy density contained in a certain interface or here a certain position. So it's just proportional to the electric field strength. And of course, people, well, it's more for the price, of course, it's a no problem. And people try then also to optimize this geometry using well, different approaches. Obviously, it's not a good idea to use such a geometry, which has these sharp corners here, right? I mean, you have always hotspots at these corners, and this is rather, well, not a stupid geometry, let's say. A better one is to use rounded edges. And this is a nice idea how you can optimize this using just a computer algorithm. This is a classical minimization of the participation function. So the computer is allowed to kind of change the geometry by changing the positions of these vertices here. And then basically for each position you can simulate the participation ratio, and then just put a classical algorithm there to try to minimize that. And then you see how this computer came up with an improved geometry. Starting from that one, you then just go towards this more rounded one, which you can understand has not so strong concentration of the electric field here in this gap compared to, for example, this one. Yeah, this, as I said, is a very important design criterion. We should dilute the electric fields to maximize T1 by minimizing coupling to TLS. So by these measurements, you can, of course, then also measure the TLS dipole moment. because you know the position of the TLS, we know the electric fields at this point, so we can just calculate the dipole mode of the TLS. And this is just a typical measurement that we get. This is our data. We get TLS dipole modes around 1 electron angstrom, which is just this canonical value, which I already mentioned in the beginning. And it's of course also compatible with basically all other experiments. For example, as done by the Maryland group here, using the superconducting resonators here, with the TLS on these capacitors. And yeah, basically you get very similar electric dipole moments, typically ranging, well, surrounding 1 electron angstrom. So yeah, you can do further things. You can, for example, try to see whether TLS are mostly at the edges of the chosen junction or mostly inside the tunnel barrier. Of course, at the edge of the tunnel barrier, you expect maybe further problems like damping bonds, contamination, or whatever. And we try to probe this basically by measuring the density of TLS in differently designed junctions. Actually, for this, we use large straight junctions because here we can detect the TLS, but they don't affect so much the qubit runtime. The real qubit junctions are these very small ones here. So here we actually exploited these straight junctions as like just a nice test object where we can put a lot of TLS inside there while still the qubit remains coherent. And you see, we just varied the geometry of this junction. For example, we enhanced the length of the edge by just using this kind of zigzag structure here on one side. And we also distinguished two edges. So one of the junction edges is always below the top electrode. This is called the covered edge, and one is the open one, which is the one which is exposed to the atmosphere. And we probed just both of these edges. So this basically varies the covered edge. And this is just a reference junction, which has the minimal edge length. Yeah, and the result which we got from these data points is basically that the TLS density is just a linear function, as good as the data gets. It's a function of the area of the junction, but it's not a function of the edge length. So, and this is maybe not so clear why this is the case, but this is at least what we find. So we don't find an excess density of TLS at the edges of the junction. They seem to be just proportional to the area of the junction. Okay. Actually, another interesting point could be that maybe there are no TLS at the edges. So this is at least one valid theory, also compatible with this data. So, and there could also be some reasons why you should expect smaller TLS at the edge of the junction. For example, here the material may have a smaller strain, so it's maybe more easier to condense in a more crystalline version here. But this is very much speculation here, and just to give you some ideas. Okay, so the reminder of this talk, I'm just presenting some remedies, possible remedies, how people try to get rid of these TLS, so how to remove the density, how to reduce the density. And the approaches in principle are quite straightforward, but clear to you, I guess. You could try to use better materials. Maybe ones which have more stable oxides, yeah, not like aluminum oxide, but maybe it's just a more stable one. And people have tried, for example, niobium, tantalum, rhenium, and also these biatomic superconductors. And you can see some examples here. So, for example, here's the average runtime of qubits using aluminium. Here is just a sapphire substrate, and tantalum. And you see, tantalum seems to behave a bit better in terms of Willis vector or in terms of measured coherence time. And actually, tantalum has been a bit of a hope during the last years, trying to improve these runtimes, these qubits. And you do get some improvement, but also you have a much harder fabrication, and it's not so straightforward as the initial publication actually suggested. Also, of course, you can change your fabrication processes. So you could, for example, try liftoff as etching. Maybe just better to sputter the metal rather than evaporating it. Maybe molecular beam epoxy or atomic layer deposition is an advantage here. This you can change. You can change the thicknesses of these layers. And actually, we found that with thicker films, you get better T1 times. You could also try to, before you expose your qubit to the oxide, where the metal oxide will grow, you could try to cap it, to cover it with some non-oxidizing inert material. This material, of course, should not contain TLS itself. And it's already not so easy to find a material which doesn't contain TLS, but people have at least tried like gold films or silver films or niobium nitride. You could also try to use trenching, we'll come to that later. Or you could also try to remove TLS, or especially on sulfates, by, for example, exposing the chip to ultraviolet light. So the point actually I want to make here is that these experiments are really difficult. It's always tricky to get a statistical clear improvement when you make these qubits from different materials. First of all, it will be difficult to figure out what exactly is the difference between, because different materials require much different purification processes, much different chemicals, for example. So many things are changing here, and it's always unclear what gives the difference if you can observe it at all. Because, as I said, qubits have a very large intrinsic spread by chance coupling the different TLS. So it's really hard work to try to improve this now. And this is actually the reason why we have significantly slowed down in our progress coming to better and better qubits. So some further ideas here. So I mentioned that you could try to trench this substrate. The idea here is that if you expect that you have TLS basically in the substrate or the substrate vacuum interface, and I told you there's many TLS in the substrate vacuum interface, why not just remove the substrate in the gap here between, for example, the gap of resonator? And yeah, you can do this using, for example, this wash process here, just etch deep into the silicon here, and then, for example, just measure again the T1 time or the relaxation, the Q factor of this resonator, an untrenched or trenched version. And well, you typically do get some changes, but I can say that you typically don't get an improvement. So one reason why you don't expect an improvement here is, well, you have of course much more surface here actually. So the substrate itself is actually rather clean. It should be crystalline, there should not be too much going on there. But if you now etch it down, first of all, you will have a very rough structure here, the field will have local maxima here, and also the total surface will be increased. So at the end, this is not a good idea. People also tried this with a qubit. This is actually a transform qubit that has also been etched down with this Bosch process here. So the junction is actually freely hanging. Yeah, there's just a junction hanging here on this very long bridge here. And this actually did increase the dephasing rate of the qubit. So there was a strong effect from the, what you believe are magnetic spins on the surfaces of this qubit, because these are seen as the largest culprit for the qubit dephasing in a flux-dependent qubit. And so this is the reason why this qubit at the end also did not really show any useful improvement in the T1 time. Yeah, similar things you can do in this experiment. I think this was actually an accident, so the qubit just somehow coiled up here, but then at the end you also had a nice free hanging structure. Yeah, but again, it's not really a solution here. Another idea is, of course, to maybe use a crystalline substrate as a dielectric in your capacitor that you need for the transform qubit. And one idea here is to basically use a silicon fin, or like a wall of silicon that you just etch from the silicon substrate, and then you can evaporate the electrons here and there, and then the electric field of this capacitor just basically goes only through this crystalline substrate. This is a possibility, but again, of course, well, it was not possible with these experiments to generate any significant improvement in T1 again. This is a picture I found on a video from the IBM group. This shows a zoom into the Eagle processor, the quantum processor, and I cannot guarantee, of course, that this is really what they do. I mean, this can just be like an artistic picture, but I think it looks reasonable to me from a point of view, because the transform qubit here, the two capacitor plates and the junctions in between are now like going in the third dimension. So you like have a very thick, let's say, capacitor electrode here, and you see the field here would be like more the field of a plate capacitor, which is more homogeneously concentrated here just between these two electrodes. But okay, I don't guarantee that this is true because you don't get this inside information from IBM. So people also tried to, as I said, work on these adsorbates that we expect to have here, and there is, for example, can be oxygen or hydrogen just bonding here to the aluminum oxide surface. And you could, for example, now try to put your sample in ultra-high vacuum, like in this sample holder that you can pump out. And there's a seal. Actually, there's a nice work by Robert McDermott. And actually, this seal here to make it ultra-high vacuum compatible has been explosion welded. So you used some explosive to melt this this cover to the sample holder, and then you were able to just pump it out. And also they had like a UV LED here, so the ultraviolet light was also the idea that you could desorb the spins by the UV light here, and then they would just float around and be collecting here in some gaps or in some sorption pump, if you wish. And so these experiments have been done with DC squids, which have a very high sensitivity to these surface spins. And in fact, you could see that if you operate them not in normal vacuum, but in this ultra-high vacuum, which in this case actually was backloaded with nitrogen, with inert ammonia, you see in fact a small density of this flux, a smaller flux noise here, so basically a small density of the surface spins. So this is a very nice first indication that you can really dissolve these spins, and that they're also the origin of this flux noise. And but it has so far not done with qubits. But here is an experiment which did a similar thing with the qubits, done by the IBM group. Again, they have a sample holder which is kind of vacuum tight, despite this O-ring here. And again, you could then try to see whether some exposure to ammonia improves things, whether some ion bombardment helps here or some UV light. And this is basically the data. So the colors don't really show here, but maybe you can see there's a little bit of a darker shading in this lower triangle. So what you see here is actually, for example, the decay rate of the qubit before you make these fancy things and after you do this. So what you expect, if nothing changes, you just expect like a straight line here. The T1, for example, before is the same like T1 after. Yeah, and you see, often you try different things. For example, here you try this exposure to sulfur hexafluoride, and here you use some UV light. So basically you see that still all of these points like to accumulate here close to this diagonal here, which means that there's not a change before and after, or at least only for some cases some significant or some relevant change could be observed. But again, you see this large spread here, and of course many qubits have been measured in these samples. And this is just what I said. It's very difficult to use statistics to see how your fabrication can improve these qubits. It's really a difficult game. And again, just the reason why we still don't have a quantum computer. So, talking again about these surface spins, let me briefly remind you about electron spin resonance. So, in the classical approach of electron spin resonance, you can use a resonator, which in this case is just this relatively large coil here, connected to some capacitor, some series number. And also this resonator at this voltage maximum is connected to some probe material. Now what you do is, this probe material, if it contains spins, the energy of the spins depends on the magnetic field which you apply. So you know probably that the energy of a spin just increases linearly with the magnetic field, and so at some field you should bring the spins in resonance with the resonator. If the spins are at the same frequency as the resonator, they like to absorb the energy from the resonator, and the resonator is a smaller Q factor.
Like in previous 5 minutes, it seems like you've talked about it is the case that you've talked about a different type of two-level systems, which are magnetic spins, and they couple to flux, well, to flux degree of freedom of your qubit, whereas before we were discussing TLS that couple electrically. And then my question is whether all of the previous discussion and, let's say, the characterization of statistics, of coupling, of the distribution of strengths of coupling, of typical energy scales with respect to temperature apply to magnetic spins.
Yeah, thank you very much for this point. Actually, yes, I'm talking now about in principle, a totally different thing. Before I only talked about this charged TLS, which we assume and pretty much know are interacting with the electric field of the circuit. And now I'm talking about magnetic spins.
Yeah. Maybe the first question I would like to ask is whether those magnetic spins have the same order of magnitude contribution to the, let's say, quality factor, and if so, how can you deduce?
Yes, also a very good point. If you ask me, I say, well, I think you can ask anyone. Most people would say, no, the spins do not so much affect the T1 time of the qubit like these TLS defects. One reason is obvious. The typical transform qubit doesn't have a large magnetic coupling. I mean, there's DC split there, but the electric field in this DC split is not large because it's a large thing. It's in a micrometer. The field is just even on the wires itself, not strong enough to get a strong interaction with a single spin there. And this is, I guess, a very good argument why you not so much limited, the front of the qubit is not limited by the surface spins. But the phasing rate may be. In some cases, it certainly is. As I said, these spins may fluctuate, just change their rotation, and they generate flux noise. And this can be observed in qubits. For example, in flux qubits, you see very nicely the phasing rate as this linear increase when you go away from the symmetry point, which can be nicely explained just by the coupling of the surface spins. That's right. But for the conventional transform qubits, I think the understanding is that it's not the surface spins which dominate the T1, it's the charged qubits. Okay, so you can detect these spins by just using a resonator and seeing the quality factor as a function of magnetic field. Yeah, people also tried this. This is another experiment by Pavel Bushev when he was in Karlsruhe. So he actually used one crystal which contained many spins, so-called erbium-doped, I don't know, erbium-doped. Well, some doped material, let's say. In the background you see some LC resonators. So basically you can just put this material on these resonators and then you have some interaction between the spins in this material and the resonator, magnetic field. And then of course you're exposed to the magnetic field, and again you see at some point we tune the spins basically through resonance with the resonator. The resonance are these horizontal lines here, and again the anti-crossings indicate the point where now you got the spins in resonance with this resonator. This was just an introduction, a reminder about ESR, and now we can now use superconducting resonators like and see whether we find indication for surface spins there. And the idea is the same. You make a resonator, a conducting one, and you expose the magnetic field. And you measure the quality factor of this resonator as a function of the field. And you see the inverse quality factor basically has very pronounced peaks at certain magnetic fields. And if you now use different resonators at different frequencies, you can do this measurement here where you just see now the frequency dependence and the magnetic field dependence of these points where you have these spins in resonance with the resonator, because this is what these peaks indicate. And you see here a very typical picture now from the spin physics. So you see that some of these spins actually at the magnetic field have zero transition frequency, and others have actually some kind of zero field splitting, as you say. And if you look closer here, this is a very well-known frequency. This is a frequency of 1.44 gigahertz, which is very well known to come from the atomic hydrogen. This is the hydrophile interaction of the hydrogen atom, which just has a zero field splitting at this 1.4 gigahertz. And so this means that this measurement was the first time able to really identify the origin of these spins. Yes?
Jürgen, this is an old story, and I explained to many people many times already that this interpretation about atomic hydrogen is very debatable, not to say doubtful. ESR people are completely sure that these peaks do not belong to atomic hydrogen, but they belong to trapped electrons. Trapped electrons. Atomic hydrogen cannot be formed in this system. The only possibility is that in the course of lithographic technology of this device, it could be formed occasionally by means of some high energy chemistry. But the probability of it is very, very low. So this old interpretation of hydrogen as atomic should be considered with certain strong doubts.
Interesting. Okay. Well, maybe I think you will find this paper very interesting because they also have very many thoughts about how this hydrogen actually is able to stick to the surface of this aluminum oxide.
It is unable. Oxide can be atomic hydrogen.
Well, actually, when you read this paper, they argue, and I mean, it's not my argumentation, but at least what they say, is that the aluminum oxide surface acts like a catalyst for the dissociation of water.
It is impossible. If it is dissociation of water, it is not atomic hydrogen. It is proton in this case. And proton has no free electron. It is impossible to arrange dissociation for atomic hydrogen and OOH that occur by means of oxide. It's only possible on transition metal.
So you say it's impossible that hydrogen sticks to the surface of aluminum oxide?
Only as a problem. H plus.
Yeah, okay. Okay. Okay, so clearly I'm not familiar enough with this kind of
This should be discussed sooner or later with Kubarkin, not with you. I understand.
Yeah.
I simply.
Yeah, no, this is fine with me. No worries. Yes. Okay, this is an interesting point. Still, I think it will be interesting to hear at least the arguments. And they have really a lot of arguments about this. They even explain the mechanism by which this proton sticks to the surface. Maybe I'm just also, well, as I said, I'm not an expert in surface physics, and yeah, I think I just cannot say much more about this. But yeah, it sounds interesting. Thanks. But at least, okay, at least the data really looks convincing. To the naive experimentalists, you see just these kinds of curves here. And they clearly don't go to zero, right? They end up somewhere. And this is pretty suspiciously close to this 1.4 gigahertz of atomic hydrogen. I'm not going to argue here because I'm really not in the position to be able to do this. But at least this is the theory presented here. Another nice thing, actually, well, we are at the end of the time, so maybe I just, I could show much more of this, but probably not. Okay, so actually we are at the end of this lecture. I'm just feeling through the rest here, and I think there's not much you are missing. I mean, there's nice data to miss. And this is, of course, a nice picture. This is kind of my motivation picture, which I have hanging on my office door, just reminding me how interesting things you can find by just looking into amorphous materials. Okay, thank you very much for your attention. If you and if you're interested, I hope it was interesting. And yeah, have a good time.
So, is this your last lecture?
Yes, this was the last one.
So this is your last lecture, so let's start again for the series.